Okay, so let us first recall what we were discussing yesterday, so that what we discussed yesterday, series of real numbers. What is a series of real numbers? You have infinite sum a1 plus a2 plus a3. So addition of infinitely many numbers, right? Boolean, mute yourself. Bhushan. So series of real numbers is an infinite sum, right? If you are adding infinitely many numbers, and a1 is a first term, a2 is second term, and so on. An is nth term of the series. So an is nth term of the series, an. And here n is from 1 to infinity. You can start n from 0 to infinity depending on your series, right? So if an is a series of real numbers, then and xn is equal to a1 plus a2 plus a3 up to an for each n. That means if I define xn, x1 is a1, x2 is a1 plus a2, x3 is a1 plus a2 plus a3. Then xn, then and xn is equal to, then xn is called as, what xn is called? Sequence of partial sums of the series En. That means we are taking partial sums, not all sum, partial sums, and that gives us a sequence x1, x2, x. So series En is convergent if and only if sequence xn is convergent, right? And limit of sequence xn is actually sum of series, right? So the limit of sequence xn is exactly the sum of the series, and therefore when we want to check the convergence of series, sometimes it is straightforward calculation of limit of sequence of partial sums, right? So also we saw example is series 1 upon n to n plus 1 is convergent, right? This series is convergent. We also discussed that series 1 upon n factorial is convergent, right? Also we discussed that series 1 by n square is convergent, right? Also we discussed that series 1 minus 1 raised to n is divergent. So series minus 1 raised to n is divergent. Right. This is some examples. These are some examples which we already discussed yesterday. So also we saw important result yesterday. What was that? If series an is convergent, then limit n tends to infinity an is 0. Right, so what is an? An is nth term of the series. An is not sequence of partial sums. Sequence of partial sums is something different. A1 plus A2 plus sum up to an. Right? Then xn is sequence of partial sums. And what we are talking about, series is convergent, then limit of an must be 0. Right, so limit of an means limit of nth term, not sequence of partial sums. Right. So what is the contrapositive statement to this? What is the contrapositive statement to this, or equivalent statement to this?
If an is not 0, then series
Right.
an is divergent.
Limit an is not 0, then certainly series an is divergent. This is obviously true, and so that we saw some examples. What can you say about series n plus 1 upon n plus 2? Right? Is it convergent? Is it convergent? Yes. So what is an here? Nth term of series n plus 1 upon n plus 2. Right. Therefore, what is limit of an? What is limit of n plus 1 upon n plus 2? What is this limit?
1.
Limit is 1 and limit is not 0. Therefore, by this theorem which we proved yesterday, right, can we say that series n plus 1 upon n plus 2 is divergent? Right? Is it clear?
Yes, sir.
Right. So immediately we can understand this. So now I will give you one more series 1 plus 1 by n raised to n. N is from 1 to infinity. Does it converge?
No.
No.
Not convergent, because here what is an? An is 1 plus 1 by n raised to n, right, for each n. And therefore what is limit of an? Limit of an is, what is limit of
E.
an is e, which is non-zero, right? Therefore this series is divergent. Therefore series 1 plus 1 by n raised to n is divergent. Divergent means in fact all terms are positive, so the sum is infinite basically. Right. So what can you say about series 1 raised to 1 by n?
Divergent.
Because here n is n raised to 1 by n. And you know that what is limit of an?
1.
1, which is non-zero. Right. Therefore series n raised to 1 by n is divergent. Right. That means if you add all these numbers from 1 to infinity, 1 raised to 1 by 1, 2 raised to 1 by 2, square root of 2, cube root of 3, fourth root of 4, and so on, that sum is infinite. So now okay, so given a series an of real numbers, when I say a means n start from 1 to infinity or depending on the series, so real numbers, the series of suppose n is a series of real numbers. Okay, now what, let xn be a sequence of partial sums of series an, sequence of partial sum. Therefore, what is the nth term of sequence? What is the nth term of sequence? right? Nth term of sequence is a1 plus a2 plus up to an. Now, if series an is convergent, then can I say that sequence is convergent? Can I say that
Yes.
sequence xn is convergent? Xn is convergent, right? And therefore, can I say that xn is a Cauchy sequence?
Yes, sir.
Therefore, xn, because every convergent sequence is Cauchy, so xn is a Cauchy sequence, right? So now, if series is convergent, certainly we say that sequence is Cauchy, xn is Cauchy, and therefore, by definition of Cauchy for given epsilon, there exists k, right? By definition of Cauchy sequence for given epsilon, there exists k such that what? Xm minus xn is less than epsilon for all m greater than n greater equal k. So if m and n are equal, then difference is 0. So the point is, if m and n are not equal, if then one of them is bigger, another is smaller. Suppose m is greater than n, right? In fact, for all m n greater equal k, this is true. So for all m n greater equal k, this is true. Fine. Is it clear? What I have written is clear. Xn is convergent, therefore it is Cauchy. So by definition of Cauchy sequence for given epsilon, there exists k. Fine. That means, but what is xm? What is xm? So for m greater than n, what is xm? Can you tell me what is xm?
A1 plus A2 up to AM.
Right, and I am saying that key m is greater than n, so in between there is some an. Right, suppose I want to m is equal to 15 and n is equal to 10, and I want to write down xm minus xn. So what is a 15? So it is a1 plus a2, a10 plus a11, right? In between an, so an plus 1 up to am minus xn, a1 plus a2 plus a up to an, right? This difference is less than epsilon for all m greater than n greater equal k, right? So one of them is bigger, whichever if n is greater than m, then I can interchange the role of m and n, no problem. But what is the difference? What is this difference? You tell me what is the difference up to a1 plus a2 plus an. These terms are common, so what should be the next step?
They will be cancelled out.
Right, so an plus 1 plus an plus 2 up to what? Am is less
AM.
than epsilon for all mn greater equal k and m greater than n. If equal, then not an issue. And so finally what we have proved, where we reached, or I can write this as absolute value of summation of ak, k running from n plus 1 to m. This is less than epsilon for all m greater than n greater equal k. Okay, so can I make some general theorem from this? We have proved something, what we have obtained, and what will be the statement of theorem. From this, I want to define some theorem. What I assume, if series an is convergent, this was my assumption. Series an is convergent, right? Then what I found at the end, what I found at the end, there is no, now there is no xn in between, right? We introduce a sequence of partial sums xn, but ultimately at the end we'll get something in terms of epsilon and terms of series. So what should be the statement now? If series an is convergent, then what should I say? See this, our explanation. We started with series an is convergent, and where we reach at the end, where we reach. Can you make the statement? If series AN is convergent, then given any epsilon, we can produce K such that what? We can produce K such that the summation AN plus 1, AN plus 2 up to AM is less than epsilon for all M greater than N greater equal K. Right? So is it correct statement?
Yes, sir.
Right, and that is what we have proved in the previous discussion. Right, and what is the proof? See above discussion. Right. So in the above this discussion, we already proved this, right? And this is called as a Cauchy criteria for series. Cauchy criteria for series, right? So because we are using Cauchy property of sequence, and ultimately we get this. Now, what is the significance of this Cauchy criteria for the series? And we already discussed this. Xn is equal to 1 plus 1 by n, right? What can you say about this sequence? What can you say about this sequence? Is monotone increasing?
Yes, sir.
Right, this sequence is monotonic increasing, and we have proved that Xn is not Cauchy. Did we prove this? You
Yes, sir.
check the previous calculation. Xn is not Cauchy, right? And therefore Xn is not. Now you go back and see the previous notes. Why this is not Cauchy? This is exercise and write it again. Why it is not Cauchy? So Xn is not Cauchy, therefore Xn is not convergent. Right. This is clear. Now uh, consider series 1 by n. N is from 1 to infinity. Right. Now consider the series. Now our question is, does this series converge? Does this series converge? And what is your answer? What is your answer?
Maybe yes, because the an term is the limit of that one is 0. So
Okay. Okay, what is this xn now? Then xn is sequence of partial sums for series 1 by n. Is it right? Xn is a sequence of partial sums for this series a 1 by n. Is it correct?
yes, sir.
Okay, now is xn
Yes,
convergent?
sir.
Is xn convergent? Is xn convergent?
No.
No, sir.
This is already discussed, right? Same series I am taking here, same sequence. So this xn is not convergent. So xn is divergent, and therefore what?
Series is divergent.
Series is divergent, right? Series is divergent. This is important result for us. Ki series 1 by n is divergent. Now, next question I would like to ask.
But sir,
Let me ask first question.
for an
If limit an is if series an is convergent, then limit an is 0. You want to say this? You wanted to say this, right?
yes sir, yes sir.
My question is converse true? This is a one-way statement. Implies, then implies, not other way. Is converse true? What is converse? That
Limit of
means
Yes.
an is equal to 0
limit
implies that series is
0.
convergent.
Does this imply series an is convergent?
No sir.
And what is your answer now? Answer is
No.
no. Why?
Because we can show a series for which an is limit of an is 0, but series is not convergent.
Right, exactly. So we can produce a counter example. Right. When we say some statement is false, one counter example is sufficient. Right. When I say ki every student in the class is brilliant, then if we produce one counter example ki fails, then we say the statement is not true. So, and what is example? So example is series 1 by n. So in this case, what is an is 1 by n. So limit an is 0, but the series an, which is 1 by n, is divergent. And divergent we have proved because how we prove divergent? Because the corresponding sequence of partial sums is not Cauchy and hence not convergent. So all that thing we have already discussed, right? And therefore this example is interesting because limit an is 0 does not imply series is convergent. That you should remember. This is very important statement, right? So remember this key and try to understand the meaning of statement. Key statement, if P implies Q means if P is true, then Q is true, not converse. Converse may not be true, right? So if limit an is 0, it may converge, may not converge. So for example, so yesterday we discussed this example 1 by n square. Is it convergent? Right? We have proved that it is convergent. And what is an? 1 by n square. What is limit of an?
0.
In this case, limit is 0, series is convergent, but not the general statement is not universally true. Ki limit n is 0, then series is convergent. Right? Maybe converge if limit n is 0. So note that. So if limit an is equal to 0, then series an may converge or may diverge. Nothing can be said, right? So therefore limit an is not equal, but if limit an is not 0, then definitely, then what?
Series is divergent.
Series an is divergent. So therefore checking limit of an is useful if series is divergent. Otherwise it is not useful. This criteria is not useful at all. Correct? Okay, so now second point, if uh, an is greater equal 0 for all n. Suppose all terms are non-negative. It may happen that terms of series are negative, but suppose all terms are non-negative, and let xn is equal to a1 plus a2 plus an, right? Then can you say that xn is monotonic increasing?
Yes, sir.
Right, because if you add one more an plus 1, then that xn plus 1. Why? Because xn plus 1 is a1 plus a2 plus an plus an plus 1, which is, so up to this it is xn, so it is xn plus an plus 1, and an plus 1 is non-negative, therefore this quantity is greater or equal xn. So it is monotonically increasing. So if xn is not bounded above, then what will happen? If xn is not bounded above, then what will happen?
Series will be divergent.
If xn is we are looking at this instant we are looking at sequence. So if xn is monotonic increasing and not bounded above, then limit of xn is infinite, so divergent, right? And therefore, what about the series a? Actually infinite, right? That means series will be divergent. So that is a simple observation from the uh, sequences, right? Now we want to generalize our class, right? So if you look at series 1 upon root n, or series 1 upon n, or series 1 by n square, or series 1 by n raised to 3 by 2, so which of them are convergent? Right, here power changes. Here power is half, here power is 1, here power is 2, here power is 3 by 2, right? Or series n raised to 2020. What about this series? So do you get some certain general idea whether the series converge? So let us see this, what happens. So okay, now so let p greater than 1, right? P is some positive number greater than 1, then consider the series 1 upon n to the power p. N is from 1 to infinity, right? Now what is the condition on p so that series is convergent, or if p greater than 1, does the series converge? We will generalize our result. See, we know that 1 by n is divergent, 1 by n square is convergent by our yesterday's discussion, but we don't know 1 upon root n, or we don't know 1 upon n raised to 3 by 2 or n raised to 20, right? So we'll generalize this problem and try to find the for general p, whatever power p now, right? But we are assuming now p greater than 1 for instant, and see what happens whether the series converge, right? So our question is, does series converge, right? So this is some general bigger question now, not particular p. P could be 3 by 2, P could be 100, whatever it may be. Okay, so try to use the basic knowledge, convergence of series. So let xn is equal to, construct the sequence of partial sum. So what is the first term? a1 plus a2 plus a3 up to an, right? But what is a1? 1 upon 1 to the power p, 1 upon 2 to the power p, plus 1 upon 3 to the power p, 1 upon n to the power p, right? Is it clear what I am writing?
Yes, sir.
Yes, sir.
Then Xn is a sequence of partial sums of series 1 upon n to the power p. Right, this is a sequence of partial sum. Now we are interested in whether sequence converge. If sequence is convergent, we'll declare that series is convergent. If sequence is divergent, right. And what is the one more observation for this sequence? Xn is monotonic, increasing. Xn is monotonic, increasing. Am I right?
Yes, sir.
Yes, sir.
Because each term is positive, so if you add more terms, the xn plus 1 is bigger. Okay, recall this, which we have already discussed. If xn is monotonic sequence and suppose xn is a monotonic sequence, if xnk is a subsequence of xn and limit of xnk is alpha, then what is limit of xn, or is xn convergent?
Then xn converges to alpha.
Right. Did we prove this result before?
Yes, sir.
Right. Because if, but in general, is this result true?
No, sir.
Right. Because if sequence is monotonically increasing and if one of the subsequence converges, then original sequence converges. In general, if one subsequence conversion does not imply sequence converge, for example, -1 restraint and some other, then not sequence xn is convergent and limit of xn is also alpha. So this is what the important result we have already proved. Right, now we'll make use of this result to prove this. So what is our sequence xn is monotonic increasing. So we will check that we will uh, check that there is a subsequence. There is a subsequence xnk of xn such that xnk is convergent, right? And then from that we will be able to declare that our sequence xn is convergent and hence corresponding series is convergent. The idea is clear. What is the strategy? Do you understand what is our strategy?
Yes, sir.
And why we are using this strategy? Because our sequence xn is monotonic increasing. That's why it is possible to apply this strategy. Okay. So what x1? What is x1 here? What is x1?
1
Only
upon
for
1.
right. Okay, now I will look at x3. 1 upon 1 to the power p plus 1 upon 2 to the power p plus 1 upon 3 to the power p. Right? So this is 1 plus. Okay, so I will replace 2 to the power p, 2 to the power p. So which amount is larger now? Is the latter amount is larger?
Yes, sir.
Because I am replacing 1 by 3 to the power p by 1 upon 2 to the power p, which is a larger quantity, right? And therefore this amount is larger. But this is 1 plus 2 times 2 to the power p, right? Which is ultimately 1 plus 1 upon 2 to the power p minus 1. Fine. This is x3. Now I will look at x8. Why I am looking x7? Why I am looking at x7? So that I will tell you later, or What is x7? 1 plus 2 to the power p, 3 to the power p, 4 to the power p. So 1 upon 5, 1 upon 6, 1 upon 7. Right, this is my x7. But up to this it is x3, right? And this amount already we have verified that it is less than something. And then second bracket. So let me write down it in detail. So fine. So but this first bracket we have already verified that it is less than 1 plus 1 upon 2 to the power p minus 1 plus. Think about next bracket. In this next bracket there are 4 numbers. Among these 4 numbers, which number is the largest?
1 upon 4 raised to p.
Right, 1 upon 4 to the power. Please, I will replace every number by this same number. And these are 4 numbers. So right, and certainly amount is larger. So what is it? 1 upon 1 plus 2 to the power p minus 1 plus 4 times 4 to the power p. But 4 can be cancelled. So what is it? 1 plus 1 upon 2 to the power p minus 1 plus 4 to the power p minus 1. But 4 is 2 square, right? So I can write it as 1 upon 2 to the power p minus 1 upon 2 to the power p minus 1 whole square. Am I right?
Yes, sir.
Right. So I want to express it in terms of 1 upon 2 to the power p minus 1. Fine. But what is x7? x7 is x2 to the power 3 minus 1. All right. And what is x3? x2 to the power 2 minus 1. And what is x1? x2 to the power 1 minus 1. Now do you understand which subsequence I am looking at? What is my nk? Right? Let nk is equal to. Then by induction we can show that what by induction what we can show xnk
xnk
x2 to the power k minus 1 is less than or equal to what? Now compare with previous. 2 to the power 3 minus 1 is less than what? 1 upon 1 by 2 raised to p minus 1, 1 by 2 raised to p minus 1 raised to 2. So we stop at 2 here. This 2 is important. Raised to 2. In previous step, this is raised to 1, power 1. Right? So what is here now? What is in general? Less than or equal to?
raised to k minus 1.
Right. So 1 plus 1 by 2 to the power p minus 1. 1 upon 2 to the power p minus 1 whole raised to 2. And up to 1 upon 2 to the power p minus 1 raised to k minus 1. This is the inequality for each k belongs to n. So you should prove this by induction. Verify this by induction. Now you know how to apply induction and you can verify this. Right. Okay, what further? What should be my next? My ultimate aim is what? Remember what is our ultimate aim? Our xn is monotonic increasing. We wanted to produce a subsequence which is convergent. So we will check that there is a subsequence which is convergent. So now we are looking at this subsequence xnk, that is x2 raised to k minus 1. and we want to verify that or check whether this subsequence is convergent. So how to check this? Right? Now x2 to the power k minus 1, by previous step it is 2 to the power p minus 1 plus 1 upon 2 to the power p minus 1 raised to 2, right? 1 upon 2 to the power p minus 1 raised to k minus 1. Okay, this step is clear.
Yes, sir.
Yes, sir.
Right, now this is like a geometric sum. This is geometric sum. So 1 plus r to the power k minus 1 is, what is it? Am I right? And here r
Yes.
is
Yes, sir.
to the power p minus 1. Here r is this. And r is less than 1 certainly. Therefore, x2 to the power k minus 1 is less than or equal to this, which is what? By this geometric sum, 1 minus 1 by 2 to the power p minus 1 whole to the power k divided by 1 minus 1 by 2 to the power p minus 1. This is r. Correct?
Yes, sir.
Yes,
Fine.
sir.
So this is 1 upon 1 minus 1 by, okay, let me write it in some more simpler form. So 1 upon 2 to the power p minus 1 into 2 raised to p minus 1 into this bracket raised to k. But this bracket is less than 1, right?
Yes, sir.
Right, and this number is a constant now because we have already fixed our some p. I have chosen some p greater than, so this is a constant, right? So what can I say? Therefore, x n k. What is x n k? X2 to the power k minus 1 is bounded above. Is bounded above. Am I right?
Yes, sir.
This
Yes,
subsequence is
sir.
bounded above. Very good. Now, is it convergent?
Yes, sir.
Right? Why?
By
Because
monotone convergence theorem.
x n k itself is monotonic increasing. Right. Therefore, therefore subsequence x n k. What is it? X2 to the power k minus 1 of subsequence of sequence xn is convergent. And therefore we can declare that xn is also convergent. Okay, is it clear now? Sequence xn is convergent. Fine.
Yes, sir.
Therefore, can we declare that the corresponding series is convergent?
Yes, sir.
Yes, sir.
Right. So therefore, series when to the power p is greater than 1 is convergent. Remember that here p is greater than 1, therefore p is greater than 1, therefore r is less than 1. 0 less than r less than 1. Why? Right? So because p is greater than 1, that p greater than 1 plays important role here. Fine. Okay, so therefore, what can you say about series n to the power 3 by 2? Is it convergent? What is p here? Right? Am
Yes,
I
sir.
right? Right, and therefore this is called as a P series test. So this test is called as P series test. If P is greater than 1, then series is convergent. Right. So this series is convergent. Certainly. Now you look at 1 upon n to the power 20. Is it convergent? So what is P here? Convergent. Right? So in because we have proved the general result. If once your P is greater than 1, series is definitely convergent. Sum is finite. But what about if P is less than 1? What about if P is less than 1? So next, if P is equal to 1, then series 1 upon n to the power P is 1 by n. Is it convergent?
No.
Is
No, sir.
divergent. This we already proved. If P is equal to 1, then series 1 by n is divergent. So that is already done. Further, if 0 less than P less than 1. Right? Now if P is less than 1, then for natural number n, what is the relation between n to the power P and n to the power 1? Which quantity is larger and which quantity is smaller?
N is larger.
N raised to 1 larger.
Right, n raised to 1 is larger. Fine. So, therefore, 1 upon n is smaller than 1 upon n to the power p. Right, for all n, because I am assuming p is less than 1. That is my basic assumption, not in general. Fine. So, okay. Is it clear? Now
Yes.
Yes, sir.
consider series. Consider series 1 by n and series 1 upon n to the power p. Right. Let xn is equal to 1 plus 1 by n plus 1 by 2 plus 1 by 3 plus 1 by n. Right. And consider another sequence yn 1 plus 1 upon n to the power 2 to the power p plus 1 upon 2 3 to the power p or 1 upon n to the power p. What is xn? What is xn? Is a sequence of xn is a sequence of partial sums of series 1 by n. Second point, what is yn? What is yn? What is yn?
Sequence of partial sums of series 1 by n raised to p.
Right, very good. Okay, now third observation, what is the relation between xn and yn?
Xn is less than equal to yn for all
Very good.
cases.
Because for each n, 1 by n is less than equal to 1 by n to the power p because our p is less than 1. So therefore, if you compare xn and yn, 1 by 2 is less than 1 by 2 to the power p, 1 by 3 is less than 1 upon 2 to the power 3 to the power p and so on, and therefore less than or equal to for all n. Correct? Fine. And now, so I am using basic knowledge. I am not using anything hi-fi concept or not any rocket science. So just basic fundamental definition. So whatever we discussed so far. So what is limit of xn less than or equal to limit of yn. Is it true?
Yes, sir.
Right. Now what is limit of xn?
Infinity.
Infinity. That is we have already discussed. Right? And therefore, what is limit of yn?
Infinity.
Is
Because if smaller is going towards infinity, so ultimately larger would go to infinity. Correct? And therefore, what is the seventh step? Therefore, what about the series? Corresponding series
divergent.
is divergent. Fine. So what is the moral of the story? Finally, conclusion. What is final conclusion? What is the final conclusion? Just summary of all the discussion, above discussion.
Is convergent for p greater than 1 and is divergent for p lying between 0 and 1.
Is divergent for p less than or equal to 1. And in fact, if p is negative, then so certainly it is divergent, and therefore not necessary to say that greater than. For all p less equal 1, it is divergent. Right? So this is a general statement. This is called as a most general p series test. P series test. Right? This is called as a p series test because from just observe the power of n in denominator. From that you can understand the series is convergent or divergent. Fine. So now you tell me. So what about the series 1 upon root n? Actually, this is 1 n to the power half. And what is p here?
Half.
Right? Less than 1. Can I say that series is divergent?
Yes.
Yes, sir.
So series is divergent. Right. Now, if I give you series 2 plus root n, what about this? Is it convergent or divergent? Is it convergent or divergent? So to answer this, so there is a comparison test, and we know that series 1 upon root n is divergent. So we can compare this. We can compare this with some divergent series or convergent series. From that we'll get some information. So let a n b n be sequences such that, suppose a n and b n are sequences such that a n less than or equal to b n for all n. That means a n is less equal b n such that uh, okay, I want to make this statement more general. So suppose a n and b n are sequences. So what is so if suppose there exists some k such that ki xn less equal yn, an less equal bn for all n greater equal k. Right. So an less equal bn, that means if k is equal to 10, then 10 onward, it is true that ki a10 is less equal b10, a11 less equal b11 for all n. But it may not be true for a9 and b9, or it may not be true for 8, 8 and b8. But after that k, it is true, right? So, so then, if series bn is convergent, then series an is convergent, right? And second conclusion, if series an is divergent, then series bn is divergent. That means we are comparing with another series. And if you know the convergence of one of them, right, we can predict the convergence of another. That's why we are comparing, right? And if you know convergence of one series and same is for from that we can predict convergence of. So that is a comparison. So in this case, in this previous case, so let us say this is see. Okay, this is true. That means an is less equal bn. That means bn is bigger. And how many terms are not included in this inequality? Only k terms or k minus 1 term. But that these are finitely many terms. That is not an issue. But after k, all infinitely many terms satisfy. Therefore, series bn is a bigger series. And if bigger is convergent, that means if bigger sum is finite, then certainly smaller sum will be finite. That means convergent. N is a smaller sum and Bn is larger. So if a smaller sum is infinite, then bigger sum is also infinite. That is what the comparison means. Correct? So uh, if you look at this 2 root 2 plus, okay, let us take this below. Look at this 2 plus root n, right? So 2 plus root n, and now 2 is constant, and root n plus root n, which quantity is larger now? Which quantity is larger? For example, n is equal to 1, this quantity is larger, first quantity. But if n is equal to 2, okay, this is larger. But if n is equal to 3, 4, what will happen? 3 onwards. So n greater
The
equal
right
to
hand
5.
side
Right.
will
If n is greater
quantity
equal to
will
5,
large.
certainly this quantity is larger. No doubt. Right. That means 2 plus root n is less than or equal to 2 times root n. And therefore, 1 upon 2 times root n is less than or equal to 1 upon 2 plus root n for n greater equal to 5. Up to 5, don't worry. These are only finitely many numbers. That sum is finite. We are interested in after 5, which is an infinite sum. If that is finite, then plus previous few terms, that is not an issue. Right. And therefore, we know that series 1 upon 2 root n, which is 1 by 2, we can take it outside root n. What can you about this series? Is it divergent?
Yes, sir.
Yes, sir.
Right. And therefore, what can you say about series 1 upon 2 root n, 2 plus root n is divergent? Right. Because the smaller is divergent, so larger is certainly divergent. Right. So in that way, the comparison test works. Correct? Yes.
Yes, sir.
So now I will use some examples. E to the power n. Think about this. Or series 1 upon n square plus 2n. Or series 1 upon n raised to 3 by 2 plus n. You think about this by comparison test, right? And you work out this and see what happens. So next time we'll see some more tests to check the convergence of series, right? Which test we saw? The limit an, limit of nth term, that is again a test for divergence. If limit an is not 0, then series divergent. Also p series test, that also we discuss, and comparison test. So proof is not difficult. If we will discuss proof of this comparison test, but not difficult proof, right? So next time we'll see more tests for convergence, and from that test immediately we can understand whether series is convergent, right? So is it clear?